Hi boys and girls, it's me Butch. My name is Terry David Silvercloud. If you want to know more about me, just Google my name. I have a footprint. So, today is the 1st of April, April Fool's Day. Won't get into that. I think pranks are bullying, and I don't associate with bullies, and I don't associate with anybody who pulls pranks. So if you're a prankster, get out of my life. Thank you. Goodbye. Alright, I'm 74 years old. No time for pranks. The other day, I don't want to waste a lot of time. I'm such a yacker. The other day I made a video about fire. What is fire? And I intended to do fire, heat, temperature. And I spent so much time trying to go over some basics of physics that I spent too much time and didn't get it done. I'm wasting time here again. So today we're going to talk about, I'll give you a quick refresher on what is fire because I didn't quite finish that, but I'm not going to waste time on what are waves and photons. If you want to know about that, go watch part 1, what is fire. So I'm going to be talking about photons and waves, and you're here to learn. I try to be entertaining, but this is educational. If you have a master's degree in physics, you should know all this, and this is not going to teach you anything you don't already know. This is basic advanced physics with no math. Very little math anyway. I'm avoiding math. So I started the other video. I made myself some crib sheets and notes because I get distracted really easily. I'm a bit ADHD or something. I started the other video talking about Lee Smolin and his book, The Trouble of Physics. And Lee Smolin was talking about the problem in physics that there's hierarchies that are hard to get by because people are protecting their jobs and new ideas are difficult to infiltrate into the system, as it were, but the physicists are working on it. And Lee went from string theory to quantum theory. So I want to give you a really quickie thing over that. Early Einstein and Newtonian mathematics all dealt with forces going in a particular direction and did not deal with volumes of energy very well, or any ways of talking about that. So quantum physics deals with that, and I talked about a bit how they do it. So quantum physics tries to bring things into three-dimensional reality. I didn't mention dimensions in my last video, so just so you get it into your head, dimensions are measurements. There are no misty, foggy dimensions somewhere else. Everything is happening in the here and now. Dimensions are a mathematical concept for measuring. And when you have a ordinary ruler, that's two-dimensional measuring for measuring the first three dimensions, which are width, height, depth, things that, you can describe them. You could describe this piece of paper. The thickness is pretty thin. It's in nanometers probably. But we could measure the edges, and if we knew the thickness, we could calculate the volume of this piece of paper. And it's really easy to do using 3 dimensions. Alright, now watch. What's the volume of this piece of paper? How on earth are you going to measure that? I mean, seriously, get real. This is the other dimensions. There's hundreds of other dimensions in here. But mathematically, really good mathematicians could probably describe this wrinkled up piece of paper in about 12 dimensions. They're just mathematical ways of describing things. There are no misty, foggy dimensions somewhere. There's no heaven or hell. This is hell, and if you're lucky, it might be heaven. Alright, we got past the dimensions thing, which I didn't talk before. I'm going to do a quick thing again. Waves in 2 dimensions. Where are you there? There you are. There you is. So waves on a piece of paper there's different types of waves. This is called a sine wave, one that's nice and curvy. And every one of these waves is the same wavelength and has exactly the same frequency. If you don't know about physics, you're saying, what? No, those are 3 different waves. No, they're 3 not identical waves that are like fraternal twins. The top one has very little oomph for volume. The middle one has more volume, and the bottom one has the most volume. So 2-dimensional waves are described on a piece of paper as curves, but in photons, which I talked about in the last video, we talk about energy being within a sphere. Photons are not solid particles. In the world of physics, there are things called bosons, which are a way of describing energy as if it were a particle. Einstein concluded, and we pretty much all agree now, that energy and mass, the solid stuff, are the same thing. This is just folded energy that is somehow, through the magic of physics, not magic, but it's all explainable, holding itself together as we all fly through space. We're all flying through space at thousands of miles per hour right now, and we all seem to be objects, and there's physics behind that, not magic. And this bottom ball, you have to imagine it's a sphere. Imagine it's a sphere. It is a 3-dimensional wave, and it is a photon of 686 nanometers red. That's pretty much a pure red, a wavelength of around 686 nanometers. There's reds on either side of it, variations of red. And in the world of quantum physics, the very smallest photon, the very smallest quantity which we bother measuring, is a quantum. In the plural, it's quanta. And a quantum is 1 photon of energy at that size. But a red photon is full of all these little quantum photons, the quantum physics photons, the ones that are as small as you can possibly be. So photons are a way in which we can add up energy, starting with the very smallest, teensiest photon, which fits into the bigger photons. And a photon is the Planck constant, which is a mathematically extremely small unit of energy invented by Planck, and times the wavelength or the frequency. Wavelength and frequency are tied together, and which one you choose to use will depend on what you're trying to find out. But it's easier to think about times the wavelength, because then you can think of it in size. But if you can spin something faster, that requires more energy too, so it works the same way. Did I cover that? I don't know. Did I cover that? Are you confused yet? Watch the first video, part 1. So we're going to be talking about heat and temperature today. That's what the whole gist of this video is going to be about. And I don't want it to go on for 30 minutes like the last one did. I'm already up to 8 minutes. Geez, I talk and talk and talk. So I talked about fire. What fire is a very rapid exchange of electrons. And in my previous video, I talked about a bit about atoms and neutrons and protons and electrons. So go back and watch that if you don't know what I'm talking about. So really briefly, just to do it, the universe has a little over 100 basic ingredients, and those ones that seem solid and they act like solids. The protons and the neutrons can be smashed and broken into things called quarks, and we're not going to talk about that, but they're pretty solid things, and there's very little difference between a proton and a neutron, except a neutron is pretty much electromagnetically and electrically neutral. That's because it has a neutrino and an electron that the proton does not have. The proton has a little hole in it. It didn't quite complete itself. So it's always looking for an electron to fill that hole, But the darn electron is too big. So you have to shrink that electron a little bit to get it down there. And that's really hard to do. You have to stop it. You have to stop it spinning. When things spin, they have more energy, and because they have more energy, they have more mass. I don't want to go that route because I don't want to confuse you. This is for you non-science types. Physics is about energy, matter, and motion. I'm a physicist. Actually, I'm a visual artist, but I'm a physicist. Let's not get into all that. In my old age, I'm a painter. I love physics. So where are we? So fire is a very rapid exchange of electrons, and now in an atom, if this was an atom, you may assume for electronic purposes it's spherical shaped, but they aren't. They're lumpy and they have odd shapes, which we can't see because they're just too hard for us to focus on, but they're a bit lumpy. Why are they lumpy? Atoms are built in layers like an onion, and the bottommost layer can have only 2 electrons in it, and the next layer can only have 8, and then the next one can only have 18, and it goes out until they're just fixed numbers. Excuse me. Smoking too much dope. Makes my nose run. Where are we? So, atoms, and the non-radioactive ones, there's less than 100, but they're composed of protons, neutrons, and electrons, and the outer part has electrons on the surface of the area, and not evenly spaced, but they're there. They're at different depths, which isn't important here. The important part is that there's a certain number of electrons around the outside, and there can only be so many. Now, if an atom has exactly the correct number of electrons for that energy field, it's neutral. And things like helium and argon, neutral gases, that's just the way they are. Electrically, they don't really want to be bothered with much of anything. But if you get an atom like oxygen, it's missing. It's got 2 holes, little indents in its outer surface, and it doesn't like that. And it's got 6 electrons. It would like to have 8, so it's really, really, really wants to fill those 2 holes. And because oxygen is the most abundant, really, atom on our planet, in the surface and in water, there's a lot of it around, and most of it's combined. There's all kinds of oxygen in this cup. There's all kinds of oxygen in this ball. Your bodies are composed of lots of oxygen. The air has a lot of oxygen in it. Let me just read this for you. Oxygen, symbol O, atomic number 8, relative mass 15.9994, valency of 2. That means it wants 2 electrons. Oxygen is the most abundant element in the Earth's crust, amounting for approximately 49.2% of its weight. It exists in many compounds and minerals. It also makes up 21% of air by volume and 33% of atoms in water. The element is an invisible, odorless, and tasteless gas, but is chemically reactive. It will readily oxidize other reactive elements, especially during combustion. That's all you need. It's important there. Oxidation is really named after oxygen, and oxidation is where an atom wants to grab any electrons it can to fill its holes. And when that starts happening extremely rapidly, remember I told you the electron was a bit too big? Well, when it goes like that, it gives up a teeny little bit of energy called a quantum. And one little quantum is no big deal. If you're outside and a grain of rice hit you falling from the sky, you'd say, what was that? But if a ton of rice fell on you all at once, you'd be dead. So that is fire. If enough of it happens at once, everything is getting excited at the electron level. And if the electrons are getting excited, they're hitting all the big things around it, and the big things get excited. and they start to radiate energy the size that they are or the size that they're moving. They can do both. And those are waves. And if those waves happen to fall between a distance of around 900 nanometers up to a millimeter, those are the really hot waves, the hot stove. You don't want to be touching those, especially if they're in quantity. One photon isn't going to hurt you, but when the stove is glowing red, there are thousands of photons. And remember, photons are imaginary three-dimensional balls of energy being thrown out there, and eventually they run out of steam because they keep hitting things, and that causes heat. Now, in Lee Smollen's book, he talked a lot about fallacy of ambiguity and false equivalency, so this is a really quick diversion here, which has not a lot to do with heat or fire, but I just want to clear something up while I'm here to teach you something. There's a lot of stuff going around about quantum displacement, and if I move my hand, I'm affecting everything through the entire universe. Oops, sorry about that. That's total BS. The reason for that is the first and second laws of thermodynamics, and in that area of physics, it assumes that the total energy of the universe is fixed. It's not growing, it's not diminishing. Even Big Bang, which is a totally ludicrous theory, works along that line, except it would fail because it would fail the laws of thermodynamics. That's why Big Bang is so full of crap. Big Bang is for people who don't think or aren't very well informed. That's where all this fallacy of ambiguity and false equivalencies are happening. That's what's wrong with physics today. There are so many people out there spouting wrong ideas, and you might even think I'm one of them. Check up on me. Read up on this stuff. I read up on it. I don't give a crap if you believe a single word I say. I'm trying to help you. I'm 74 years old. I could drop dead tomorrow. I could drop dead while I'm talking to you. I'm old. All right. I'm emotional. And I'm up to 17 minutes already. Where was I? So, fire is a very rapid exchange of electrons, and it's called oxidation because oxygen is so present, and it's the most common oxidizing agent that we know. It's just everywhere. Now, you don't necessarily have to have free oxygen like air around in order to have a fire, and explosives will show you that. Like if you set off TNT or C4 or any kind of explosive, your firecracker, it doesn't need the air that's around it. It has oxygen in the molecules built in it. And in order for fire to start, or any action to start, you need a catalyst. A catalyst is like the matchmaker in a love relationship. One of the most common catalysts, although it's not thought of as a catalyst, is water. Almost everything dissolves in water, and the moment it does, the electrons that were on the surface are a little more loosey-goosey, and the molecules, which are groups of atoms, sometimes they actually break apart and form what are called ions, and they'll come back together if the water evaporates. But we make a lot of use of that fact in all kinds of chemical reactions. You know, dish soap works better in water than in just dish soap. That's because the dish soap gets to stretch its long, stringy legs out in the water, which it can't really do. It's all crumbled up when it's in the dish soap bottle. Am I confusing you? I hope not. So fire is a very rapid exchange of electron. Heat is the quantity or volume that is happening from that exchange of electrons. Now another catalyst is the heat itself. If I light a match and I put it up to, oops, good going, David. I just spilled some chocolate milk. Teach me to put it on the table. If I put up a match to this piece of paper, it'll start to burn. We all know that. Why? The paper is composed primarily of carbon, hydrogen, and oxygen, and those bonds are relatively strong at room temperature, but when the temperature starts going up, I'm going to dampen this up here. When the temperature starts going up, the electrons get a bit further out of their orbits than they should be, and if there happens to be oxygen nearby, it will grab them. And the moment that happens, that electron loses a bit of energy that it gained from the heat. Remember, it got a bit of energy from the heat. It was out there a bit. It falls into the oxygen. It gives up that heat. And if zillions of them do that at once, you got yourself a fire. And I'm still cleaning up my mess here. Jeez, David, you're a dunce. Don't get old. It sucks. I'm really hurting today. I have arthritis. But I'm determined to make this video, so get it out of the way. There we go. Where was I? When a whole lot of these things are happening all at once, they're giving up a little bit of energy, which is a little bit of heat, and that heat causes more electrons to leap out, and suddenly the heat that's being created cannot dissipate quickly enough, and you got yourself a fire. Now, in the case of explosives, they don't have a fire. When you burn your bonfire, it has to get the oxygen mostly out of the air. Some of it is coming from the fuel, the oxidant. The oxidant is the fuel. The oxygen is the oxidizing agent. And carbon is what you're going to end up left over with. So it's not really the carbon in the wood, but combinations of the carbon with the oxygen. The heat's causing them to break apart. Electrons are flying around. There's hydrogen in the wood. It's flying around. It has only one electron. You got yourself a fire. And if you have certain chemicals where the only thing necessary to get them going is a really hard knock, like a really hard knock, like if when you have a pistol, you have a hammer that hits the back of really sensitive chemicals, which are called, the ones that are used are nitrates. And they're just chains of carbon, oxygen, and hydrogen. And if one of them breaks, you'll get an electron or two flying off, and several thousand of them break. You get thousands of electrons flying off. And at the moment that happened, the molecule of the nitrate wasn't a molecule anymore. It was a separate atoms. And suddenly there's a mad scramble for the electrons. It's like the end of the bar is closing and there's 60 men and 5 women, and they're all making a scramble to make an impression right then, because the bar is closing and we're doing it right now. I ain't going home alone tonight. That's the way the atoms are thinking. So you get an explosion. An explosion is just extraordinarily fast oxidation. It's so fast that it's hard to call it fire, because we think of fire as something that is continuous. And the reason for that is there's usually a supply of the oxidizing agent and the oxidant. So as long as there's a supply of wood, once the chain reaction gets going, the fire keeps going. And once you run out of things to happen, everybody's gone home, they've all made their dates, the fire goes out. I'm up to 23 minutes already. Jeez, I don't know how I do it. I find it hard to explain all these things. I'm trying really hard. So, what I really want to get on to a bit more about here is what is temperature and what is heat. So heat is the quantity of the oxidation going on, and temperature is a measure of that quantity, and there are several ways of doing it. You Fahrenheit, centigrade. Those systems are based upon boiling and freezing and simple ways of making thermometers. But a dude quite a while ago thought we need a better scale, and his name was Lord Kelvin. He created an absolute scale called the Kelvin scale, which in May this year is going to get a new definition to bring it in line with the Boltzmann constant. It's not going to change. It's just the definition is going to change. In physics, we're realizing everything is related to size and frequency and time. And I mentioned really briefly in dimensions. The first, second, and third dimensions are the measurements you're used to, and the fourth dimension is time. Any other dimension is just some artificially created mathematical concept on a blackboard. There is no misty, foggy places. The dimensions are ways of describing really complex shapes. Where was I? Did I cover it? Temperature, according to Lord Kelvin, starts when you have no motion. Absolutely none. And at the extreme end, you have the most violent motion we can possibly measure. And in between, we have the light spectrum and every other type of electromagnetic wave that exists. The universe consists of waves that are what I call the zero wave, which we can't find because there is no zero wave. But everything is trying to find absolute rest, the zero wave. And when things get really excited, they either spin really fast to take care of the energy, or they start vibrating or rotating. They have to do something to accommodate all those punches of energy, whether it's a big punch of energy hitting a little punch, which will roll this out of the way, or a bunch of little ones, and the big guy says, "Who are you?" But this thing had to absorb that energy, and this one gave it up. It might have gave up its life. If it was a light molecule, it will no longer exist when it hits something solid. It will just dissipate itself right back. The energy will be absorbed by the atom, and it will be heat. So heat covers from absolute nothing up to so hot you're into atomic bomb range. Well, that's weird, isn't it? No. We only think of temperature and heat as being a certain range in our thermometers. Heat that we can feel, this is the important part to get across to you, happens because of our structure of our bodies. Our eye cells are 1,000th of a millimeter, which is called a micron long, which is the exact width to accommodate every single color there is, including ultraviolet, which you can't see, and infrared on the other side, which you can't see. So your eyes are sensitive to heat, and they will be irritated with heat because they can detect those wavelengths. They are the same. Oops, where'd my other ball go? They are basically the same size. So, they just, this is a ball of energy. It's not solid. This is a solid something. This ball just merges itself in there and increases the energy of this thing. And this thing will either spin faster or vibrate faster. And that vibration is heat. The faster it vibrates, the higher the temperature. And the reason we are in physics ignoring Fahrenheit and centigrade and redefining the Kelvin scale, I lost track of what I was going to say there. Jeez, that was good. Is that centigrade and Fahrenheit just don't work in line with frequencies. And frequency is everything. How far am I up there? 20. I'm going to have to shut up. I don't know if I covered everything. So wavelengths are the hot temperatures you feel are between around 900 nanometers up to about 1 millimeter. Now your blood cells are about 9 nanometers, which is about a tenth. Did I get that right? Your blood cells are much bigger. They're nearly 9 times the size of your eye cells, and your nerve cells are 3 times as big as your eye cells. So your nerve cells are about 3 microns average, and your blood cells are about 9 microns average. Heat occupies all of those frequencies. Heat is things that you may not be aware of, like when ultraviolet's hitting you, you're being burned, but you're not really picking up on it until your nerve starts burning, which will be around 1 micron. And your blood cells are big enough to carry long heat waves and distribute it around your body and then let it go to keep your body warm. Now there's heating. I want to cover this really quickly, and I'm going to shut up soon. I didn't cover everything. I'm sorry, I tried. You have things like induction heating on stoves and microwaves, and the way they work is through a process called hysteresis. And when oxygen absorbs hydrogen and becomes a water molecule, it's a bit lumpy shaping, but it's also responsive to certain electromagnetic waves, and so it has resistance. It's trying to wiggle and wobble, but it's creating bigger waves, and that is also heat. So when you turn your microwave on, which has wavelengths around 12 or 13 centimeters, that's way bigger than your body cells or anything like that. But water, because of hysteresis, and sugar as well, and certain other, just not a lot of things, but there's a lot of molecules that are just the right size for that frequency. They began shaking with this frequency, like, ouch, I don't like this, get me out of here. And that shaking disturbs the other molecules around them, and that disturbance is heat. And as the heat rises, the temperature rises, and all of them start vibrating faster and faster and faster. And if they vibrate fast enough, all of them will, the carbon in particular, they will throw away all its excess, and you'll just have carbon left. The oxygen will escape into the air, the hydrogen will escape into the air, and things like your piece of bread, which is made of carbon, oxygen, and hydrogen, you'll have nothing left but the carbon. Carbon is a bisexual kind of atom. It's got 4 electrons in its outer shell where it could have 8. So it doesn't care if it gives them up or shares them. Not only that, it's an unusually structured atom, so it can be flattened out and molded, which is, well, you can do that with iron too, but the particular structure of carbon is such that when you flatten it out, it can actually become transparent. And we would call those things like diamonds. I'm getting off another track, aren't I? And I'm up to 32 minutes. Jeez, I wasn't going to go over that. What's important is with these long wave heats, even though your body cells seem not to feel them, no heat at all is wavelengths that get to be about this long. There's nothing left in your body or in the material out there that's going to shake enough. You're in the radio wave area and the gravitational wave. They are heat in their own way, but not heat that you care about. If they were intense enough, you would cook, you would roast. But they're so low level that they're just comfortable heat. And induction heating, like on your stove top, is caused by putting a coil underneath a piece of Pyrex glass or something that's not going to be affected by heat. And if you put a metal pot on there, iron, because of the way it's made, it's got these 4 bisexual kind of atoms, it starts shaking. And iron, as you know, heats up, and it's the shaking of these atoms being caused by that particular wavelength, which affects the hysteresis of that particular iron, and the heat that the iron is generating heats the water, which cooks the food. In the microwave oven, the water is being, or if there's sugar in there, you have to be careful. Sugar will react the same way. So high sugar content in your microwave can be a little risky if you ever try baking. But every other thing has got high water content. The water through hysteresis starts vibrating, and that causes heat, and the more heat, the temperature rises. Did I cover it? Jeez. This was a lot harder subject than I thought it would be to talk to you about simply, and even though I tried making myself notes, I don't know if I got it. You can ask me questions while I'm still alive in the comments if you want down there, if you find this interesting. And I'm going to shut up because I'm up to 34 minutes, and that's just a ridiculously long time. So bye from Butch in Vancouver. I hope I covered it. I definitely tried. Bye.